Hi guys, lesson 4. Lesson 4 is on Half-Life. It's not the game, although the game is amazing. I'm currently playing Half-Life Alyx in VR at the moment, so that's getting me through isolation. There was a problem in physics. At the end of the 1800s, we thought we had it all stitched up. Newton, 200 years earlier, had given us the laws of motion, and everything seemed to be deterministic. Now, what deterministic means is that if that ball hits that ball's going to move away with exactly the calculated amount of velocity. And if we know the mass and we know the time and we know the velocity of everything, then a bit like a big clockwork machine, we should be able to determine the future of all systems. Unfortunately, there was a problem, and that was radioactivity. When you look at a bunch of radioactive atoms, you do not know which one is going to decay through alpha, beta, or gamma. It's a totally random process. And when scientists first saw this, they thought, well, maybe we just haven't figured out enough and peered under the hood to have a look at the engine that's causing the radioactive decay to happen. And eventually we'll figure that out, and there'll be a nice little engine there running of some sort, and we can learn it, and then we could predict exactly which one is going to go any second. Oh no, it didn't go. It turns out that this was the first truly random thing we had ever discovered. Now, when we think of randomness, the classic is flicking a coin. And the only reason that appears random to us is that humans, in themselves, are a little bit random. We create random error as we try to flick the coin. But it is quite possible to build a machine that can flick a coin, and you tell it you want heads, and it'll flick a head every single time. So Half-Life was that first true case in the entire universe where randomness reigned. And that caused a hell of a philosophical problem. Because now, do we live in a universe that is totally random? And why do some things appear random and other things don't? And it took a while for us to get our heads around that, because one thing physicists like is, one, knowing for sure what's going on, and two, applying mathematics to it. So let's write down the first problem, and we'll say radioactive decay is truly random. You cannot tell which atom and when it will decay. The grammar on that does not sound right, but you get the idea. You don't know which, and you don't know when. So all of a sudden, physics was a little bit worried. It turns out, though, that there is a predictability to this. And what it boils down to is the following idea. If I take a graph of the activity of this, so every second I measure how many particles are decaying. We call it activity. So let's say we start and there were 1,600 decays of atoms per second. Now, one decay per second, I told you we were going to talk about becquerel again, is a becquerel. Bequerel. Also written as big B, little q. So we're going to write this in becquerel. So when I write 1,600, I mean 1,600 decays of atoms per second. So we'll set the timer and we'll start the stopwatch at time equal to 0, and we'll put a little cross that we were measuring our 1,600. Well, time's going to tick by, and over time, if we measure that, say, every hour, so 1 hour, 2 hours, 3, 4, 5. There will come a time where the decay will have gone down to, Let me get rid of becquerel a minute. The decay will have gone down to 800 because for every one that decays, there's less now, so it's slowing down. And there will come a time where we measure that time and we put a little cross. And we keep going. And there will come a time where we'll get to half of that, 400 becquerels. We put a little cross, we measure the activity of that, put a little cross. And what you find is you end up with a decay curve. This one isn't very steep, but it's going to curve like so. I'm just going to cheat and put one more measurement in there. I'm going to put the 6 in. About there, 6. And if I've done it right, that should match 200 becquerels. And I'll get my red and I'll put that in a little bit low, but you get the idea. So this term half-life comes from the idea that if you measure how long it takes to go from one value to another value, so I've gone from 1600 to 800, if I go along and I drop a perpendicular, I can measure the time that it took for half of the atoms to decay. So half-life is the time it takes for half the atoms in a sample to decay. You can also see that written. You might want to pause that to copy that bit. You might also see it written if I highlight the words that are interchangeable here. So it's the time it takes for this bit here. You can either count the atoms or you could substitute in the words. If I put that there, a little cross, you could substitute in the word activity. So it could read, half-life is the time it takes for the activity of a sample to decay by a half. So you can do it either way. You could have the number of atoms up the side here, 1600 atoms down to 800, or you can have activity written. It really doesn't matter either way, but you might see both types of questions in the future. Now, if I've drawn this correctly, if we'd started at 800, then the time to go down to 400 should be exactly the same amount of time. And if I drop a line there, I've gone from the 2 to the 4. It's a 2-hour half-life. Same is true here. Now this is where my drawings go a bit wrong. I went from 400 to 200. So again, if I bring my line across and I read the time, it should match the 6 hours. So again, the half-life is 2 hours. So we'll write that. The half-life of this example is 2 hours. So let's look at it in practical real-life situations. You remember in the previous lesson we did an example here about beta decay in the lesson 3 of the equations, and I talked about this isotope of carbon called carbon-14. Now if you're an archaeologist or you're into history, carbon-14 is a miracle for you. So let's give an example, and this is called carbon dating. You may have heard of the term. This is what it means. So it's tens of thousands of years ago. You're in the woods. Ugg is going along, and Ugg decides he's going to chop down a tree. So Ugg chops a tree down. He carves it into a canoe. So there's Ugg, and he's carving his boat out, and he decides he's going to travel and find new land. So he's paddling along, and he discovers new land. And after tens of thousands of years, buried underground, archaeologists come along and we dig out the canoe. And the question is, how old is the canoe? Now, even as far back as only 200 or 300 years ago, we couldn't even agree on a year. Years have changed in length quite drastically over the past, and nobody had a common dating system, and particularly tens of thousands of years ago. So it's carbon dating to the rescue, and here's how it works. The half-life of carbon dating, the half-life of carbon-14 is 5,600 years. That means if you have a kilogram of carbon-14, 5,600 years later, you'll have half a kilogram. It will have changed into nitrogen. So we don't have half as much of this. We take a small sample of the wood. We cut a little piece of the wood out. We make it into a gas, so we gasify it. We then measure the radioactivity, and we'll use the following graph. So we'll draw our axes in, like so. And we'll have here our activity. Now this time we'll put it at 100%. And here we have 0%. And we'll mark off the 50, the 25, and the 75. Because what we're able to do is take that sample there. We know what, on the day the tree was cut down, how much carbon-14 was in that tree. I didn't mention that bit. The tree, while it was growing, was taking in carbon dioxide, and it was kicking out oxygen, O2. So its body is made of carbon, as are all biological living things. You and I and trees and everything that's alive. And because 1 in a million of these carbons here was carbon-14, then the tree itself is becoming radioactive, and it's giving off very, very low doses of radioactivity. And through modelling and measurements, we're able to ascertain, for that type of tree, how much radioactivity, on average, does it have while it's alive. And the day it's cut down, it stops taking on carbon dioxide. So now, all the time it's been there, buried underground, its radioactivity has been given off, and it's decreasing in radioactivity. And so now we can plot it. We know on day 0 what it should have been. So on day 0, so if we put here, let's put it as years. So on year 0, we know exactly what it should be, and it doesn't matter what it is, because for us that would be 100%. We then measure the radioactivity of it now. So we'll put that in red. So what we'll see is every 5,600 years, the radioactivity will be dropping to a half. So I'll put across at a half. We then know at 11,200 years, 11,200 years, double, that we will have 25%. So let's find 25%, put across. So we have our decay curve for carbon-14, like so. And so we come along and we measure the activity of this carbon. And say it's measuring at 40%. So we come across at the 40%. We drop a perpendicular line down. And we can see there that it's clocking in at around 6.5, let's call it 6,500 years ago. And that's how we radiocarbon date things. So any materials that were made from cotton, so clothing can be done, food, human bones, any biologically living thing can be carbon dated. And it's a really useful tool that's given us our history. Because if you think about it, very, very little is dated. You find a mysterious object, there's no way of ascertaining the age, apart from carbon dating it, and also dating the rocks that are around it that encased it, so that you could get the date from that. So this is half-life. Now, how I like to write out, I have my own little system that seems to work. If you're really good at mathematics, it's easy. But if you want a foolproof way, a typical question might be, if the half-life, I'll just put HL, is 1.5 hours, what is the activity? What is the activity after 4 half-lives if the original was 2 S's if the original was 2,400 becquerel. So I'm a big believer in keeping it simple. So I just write it out. 2,400, 1 decay. So I count my decays, 1. That's going to go to 1,200. That's 1.5 hours. Next, another decay. So I write it out. 600. Decay number 2 gives me 600 remaining. Now I'm at 3 hours. I said 4 half-lives, so we've got another one. So now we have half-life number 3, and now we're at 4.5 hours. And that'll give me 300 remaining. And so after one more half-life, it's nice and easy. We have 150 becquerel remaining, and that's 4 half-lives, and that's 6 hours later. So this way of doing it is handy because you can work out the time quite easily. You can also count the number of half-lives, and it gives you the remaining activity afterwards. If you are of a particular way and you're really good at mathematics, you might want to use it as x to the power of, let me get this, no, it's 2 to the power of n, where n is the number of half-lives. But I don't subscribe to that. I keep it simple. That's it. Leave your comments in the comment box. Any questions, give me an email. Take care. Bye.